Well, hello. Welcome to another episode of Fun with Physics. This is your host, Mr. Easley. The purpose of this video is to demonstrate how to solve line E on Projectile Mathematics Concept Builder within Physics Classroom, but it is also an example of how to solve a projectile motion question if all you have is a launch angle and a horizontal distance. All right, so I went ahead and set this up. So this is the original picture you could draw. For most projectile problems, you could draw a picture very similar to this and put in what you do know. Essentially, we know a distance and we know an angle. Now, the ultimate question is that you're going to have to end up solving for is, what is this velocity equal? What is this velocity going to be? And then what is time? In terms of the physics classroom, it wants to know time up and then time total. We also need to know this distance on the y-axis, or the peak distance. To solve these, this is a very difficult question in terms of this, especially in introductory type physics. And the way that you have to do this is you have to start with some things that you do know and figure out what can you say. And so that's where we would go back to, since we have an equation with d of x, we would definitely want to write that down. So you can say that distance on the x is going to equal velocity on the x multiplied times time total. You got to be careful with time total and time up because of this is of course half. So we have this equation here, and that does have, we do have at least a number we can put in there, and so I'll do that. Okay, so I put in the distance on the x, put in for there. And this is a little bit of a dead end here. We can't really go any farther. And so you could say that we've kind of used up our distance on the x-axis. And what else can we go? Well, we can jump over here to the other piece of information we have, which is our angle, our theta of 14 degrees. And I should also note one additional thing that we have that we never want to forget about is we always know that acceleration is going to be equaling negative 9.8. That's always there, and we always have that. So when we're looking at our equations, that's useful to know. But we do want to think about equations that we have dealing with theta, and we want to think about, well, what are the x and y components here? Remember, that's always a big deal. You want to be thinking about x and y components. And so we could say, well, do we know anything about velocity on the x? Do we know anything about velocity on the y? We always have to be thinking about that. And do we have some equations with that? Well, we do. And so I'll write those down. So our two equations that we have that I just wrote down here are the velocity of the y component of the velocity is equal to this original velocity multiplied times the sine of theta, and then likewise for the x, it's the cosine of theta. Now, we can put in some numbers that we have here for this, and this can help us a little bit, and I'll do that. All right, so I just did the same thing twice here with both of these equations. Basically, I took the sine of 14 degrees, which that's a number, and I rounded it to the nearest thousandth here, but it's 0.242. And since that's being multiplied times v, I just put the v in parentheses to try to make it a little cleaner here. Hopefully that doesn't confuse you. Did the exact same thing down here. The cosine of 14 degrees is 0.97, rounded off to the nearest thousandth is 0.970. Then that's times v. This is useful to us because what we just did here is now we have Vx in terms of v, and we have Vy in terms of v. And we're going to use that to our advantage, knowing this acceleration. I'll show you how to do that in a second. But the one thing that we can do here is we can start thinking about, could we put over here, could we put this in terms of our original V, which is really going to help us, as you'll see in a little bit. So I'll go ahead and do that. So we're going to say, and I will jump back to blue here. We're going to say 10.6. And then in place of Vx, this is Vx here. So this thing right here can be substituted in for Vx. We can say 0.97 V times T total. And we'll just let that go for now because we can't still really solve it. But there's going to be a way to come up with time total. And that's where our next thing is. Can we get to a point where we can figure out a time total to relate this original V, which is over here, our total velocity, and how it relates to time? And to do that, we're going to need to look at our main equations for acceleration, as we've talked about in the past. And what we're really looking for is one that involves acceleration, which would be these three. These are, of course, the main four right here. One that involves acceleration, which would be these three, because we know acceleration. And then we also want to look at one that involves time. So that would eliminate this one. And then one that wouldn't include distance because we don't have distance. So that narrows it down to this equation right here, and we'll put that on our page. Okay, so I put our equation right there. Velocity final equals velocity original plus acceleration times time. And one thing to note here is we're imagining things on the y-axis here. Remember, we think about time in terms of the y-axis and projectile motion. And so we want to add the y-axis to this. Velocity original on the y-axis. This has to do with everything is on the y-axis. Now we could take this a couple ways. We could either do time as total time. If we do total time, we have to realize that the velocity on the y-axis in the positive direction is equal but opposite. And so it'd be the velocity on the y-axis would be negative in the downward direction as it comes through here, because as we've discussed, it's going downward. And that's probably going to be the easiest way to write this. And so we would say that since velocity final would be equal to a negative velocity initial, we can substitute that in, and we can just say velocity negative velocity original on the y. This probably should say O. Initial and original I use them interchangeably. It's going to equal the velocity on the y-axis plus acceleration times time. Now, what can we put in what we do have here and what we do know? Well, we do know acceleration, and we can simplify this in terms of as much as we can, and I'll do that. So I can substitute in that acceleration is negative 9.8. I can subtract velocity original from the one side, and I end up with two negative velocities on the y-axis. VOY is equal to negative 9.8 t. Now I just need to divide both sides by 9.8, and I can solve for t. And so what we find when we do that, negatives cancel, we end up at 0.204 v original y-axis is equal to time. Now this is getting pretty close. We have a time here, and I probably could clarify that is t total, because remember we did the negative velocity final equal negative velocity initial. That would be for the t total. So we probably should clarify that that's t total. So we can see here we have like terms. And here we have something expressed in terms of the velocity. This is still the velocity on the y-axis. So we're still not a like term there, but we're close. Because if you remember, we do have the velocity down here on the y-axis. And in this situation, the original, it's the same thing. we do have it in terms of v. So we can actually substitute in where we see velocity on the y-axis, we can substitute this in, and I'll do that. So all I did here was I just took this thing right here, 0.242v, and I stuck it in place of that. So you see the ugly brackets, and that's that. We can simplify this down as we work through this. And so we would find 0.049v is equal to t total. Now we have like terms and like terms. We have two unknowns and two equations. We can do the classic substitute in again here, and we can solve for this to find time total. Actually, I think I'll just substitute in and to find this original velocity, because once we have a velocity and an angle, we definitely know how to solve everything else about this. And so what would we do here is we would take where it says t total, since these are the same thing, we would put this thing right here in place of that. So I just did that. So t total in place of that, I put what we know t total to equal. So then we can do some simple algebra to reduce that.